This is the first video of a 10 series video lecture on differential equations. The subject differential equations may be considered to occupy a central position from which different lines of development extend in many directions. If we travel along the purely analytical path, we are soon led to discuss infinite series, existence theorems, and the theory of functions. Another leads to differential geometry of curves and surfaces. Between the two lies the path leading to continuous groups of transformation and the geometrical interpretation which was discovered by the Norwegian mathematician Sophus Lie. Diverging in another direction, we are led to the study of mechanical and electrical vibrations of all kinds and the important phenomenon of resonance. In short, differential equations is a really important field in the field of mathematics, and I hope you're going to enjoy the journey as much as I did. The object of these 10 lectures is to give an account of the central parts of the subject in a simple form as possible, suitable for those with no previous knowledge of it, and yet at the same time to point out the different directions in which it may be developed. The only previous knowledge assumed is that of elements of the differential and integral calculus, and a little bit coordinate geometry might be useful for you to visualize some of the concepts that I'm talking about. Enough talking, let's get started with the first video in the lecture series. I will just start out with the following 3 equations that I have lined up here, just to introduce some notation. Well, if we look at equation 1 and 2 involving differential coefficients are simply called differential equations. Differential equations which involve only one independent variable, like 1 and 2, are simply called ordinary differential equations. Those which involve 2 or more independent variables and partial differential coefficients with respect to them, such as equation 3, which over here, are called partial differential equations. I will mainly be talking about ordinary differential equation in this 10 lecture series. In equation 1 and equation 2, x is the independent and y is the dependent variable. In 3, x and t are the two independent variables and y the dependent variable. An equation like 1, which involves a second differential coefficient but none of higher orders, is said to be of the second order. Hence, equation 2 is of the third order. Okay, I will just start out by talking a little bit about some of the applications, simple applications of differential equations. So I will be showing you some examples of how to use differential equations. The first one is called formation of differential equations. I will just abbreviate differential equations with DE. I think that's a bit more convenient. By elimination. Okay, so what do I mean by that? Well, if we have a differential equation, say y equals to a, where a is a constant, e to the power of 2x plus b e to the power of minus 2x. Well, we might say a and b are constant. Let's just say they belong to the real line. Okay, so what do we do? Well, I hope you're all familiar with the chain rule from differential calculus. If you are not, then I will simply state it here. So f composed with g differentiated is simply equal to f differentiated composed with the inner function g multiplied by the inner function g's differential. So here, let's just show you how to differentiate this one with the chain rule. We simply have that f equals e to the power of x, that is the outer function. And if we differentiate that, we simply get e to the power of x. That is one of the properties of Euler's number. G equals 2, so if we differentiate 2x. So if we differentiate g with respect to x, we simply have 2. All right. So, well, I think you might be able to see now how we get to the first derivative, we simply have a2 multiplied by a. Sorry, I'll just tell you what this is. Of course, f composed with g derivative here, and we get e to the power of 2x multiplied by 2 from this over here and from the rule over here. Okay, great. So we have that y differentiated will be 2 multiplied by a multiplied by e to the power of 2x. And in this case here, we simply differentiate in the same manner as we did over here. We just have a minus sign. So minus 2b e to the power of minus 2x. And you might see where this is going. If we differentiate twice, we simply apply the same rule as we used before. But now we have a 2 standing here, so we simply put 2 down again from the chain rule. So we have 4a multiplied by e to the power of 2x minus multiply 2. Sorry, minus 2 multiplied by minus 2 is, of course, 4. b e to the power of minus 2x. Okay, so we still want to eliminate the constants in this differential equation. So what do we do? Well, we simply say 4 multiplied by y. All the time over here we multiply the whole equation, and we can say if we take this equation here and add to this equation here, oh, let's just put a minus sign in front of the whole equation to begin with. That might be easier. Okay, we have a minus sign here. I don't want to erase that. Okay, so that's a minus sign. We simply take that, cancels with that term here, and that term simply cancels with that term here. So what we're left with is that y differentiated twice minus 4y simply equals to 0, which, if and only if, y differentiated twice equals to minus 4. Sorry, plus, because we put it over on the other side, plus 4y. So what we have done here is that we have eliminated the constants of the differential equation. And I can show you more examples, but I think it's a good idea to just start out with one example and you can practice more examples afterwards. Let me just give you another funny thing about differentials. So let's say that for any straight line, I want to talk a little bit about geometry of curves and surfaces. In geometry, we have something which we call for a curvature. And if we talk about curves, we simply say that a line's curvature is 0 if the line is simply a straight line, because a straight line does not curve at all. And how can we think about this term in a more concrete manner? Well, we simply say that whenever we want to differentiate, or whenever we differentiate any linear equation twice, it simply becomes 0. So what do I mean? Well, if we have any linear equation, ax plus b, where a and b are just constants, if we differentiate this one once with respect to with respect to x, let me put it in a more correct manner. So we say we differentiate y with respect to x. Well, we differentiate with respect to x, we differentiate y with respect to x. So we simply, the constant goes out and x is gone. So we simply end up with a, just the constant. And if we differentiate once more, d squared y divided by, take the derivative, d squared x equals to 0, because we just differentiate the constant. So as what I told you before, for any straight line, whatever, if we differentiate the straight line twice, we simply have that it must always equal to 0, because as I told you about in geometry, we have something which is called curvature, and we say that the curvature of a line is 0 if and only if the line is a straight line, because a straight line does not curve at all. Okay, that was the first lecture of the differential geometry lecture series, and in the next video I'm going to talk more about the subject differential equations.